Hello there. It's Professor Thomas, the live video. We're going to be working out problems, going over strategies, solutions, tips, how to use your calculator to simplify statistics, to make your life a little easier. So we're just going to be choosing random problems at this point, and we're going to get through some of these problems to hopefully to make everything a little easier, as I said. Let's get started. Let's take a peek at some of these questions here from 6.5. We'll probably do some problems from 6.4. This is Triola's Introduction to Statistics problem books from those problems there. Alright, so let's click on some random problems and kind of do them, see what they're talking about. Alright, it says the overhead reaches distances of adult females that are normally distributed with a mean of 202.5 centimeters, deviation 8.9 centimeters. Find the probability that an individual distance is greater than 215 centimeters. Find the probability that the mean of 20 randomly selected distances is greater than 20.20. And then why can the normal distribution be used in part B even though the sample size does not exceed 30? Alright, so let's give it a shot. First, find the probability that an individual distance is greater than 215. It's always helpful to map out what you're trying to solve. So let's do that right here. We'll write out the most important information first. That women's heights have a mean, and I should have just put mu of 2002.5 and a standard deviation of 8.9. And so if it says find the probability that an individual distance is greater than 215, then what we're really talking about, if we have a normal bell-shaped curve and the mean is in the middle, and they're saying what's the probability of getting a distance greater than 215? Well, 215 is around here somewhere. So at the bottom, right? And it's this portion. Everything greater is represented in this proportion. And so what we could use is normal CDF. Normal CDF is the thing that we use when we want to find the proportion or probability and we're giving the lower bounds. Okay, so our lower bound would be 215, but we do not have an upper bound. And so what we have to do is put in an extremely large number. Let's actually go through the steps on a calculator, and I'm going to go to second, distribute, number 2, and I'm going to put in normal. I'm going to put in my mode stat wizard. I'm going to turn stat wizard on so that you can actually see the parameters and what we're entering in. So go to second, distribute, and choose 2, and my lower bound is actually 215. My upper bound, I don't have an upper bound because it's everything greater than 215, so I have to put in a very large number. Second e to the 9, and then I have to put in my mean, 202.5, and I need to put in my deviation, which is 8.9, and we're talking centimeters. Now this is what you would get on the home screen. This is what you should have entered in on the home screen. Normal CDF, 215, 1E9 represents a billion, very large number. 202.5, 8.9, and then hit enter. And it looks like our probability is 8.08, or 8%. They want us to round it to 4 places, so we do 0.801. Got it. Got it. All right. So the next part is find the probability that the mean of 20 randomly selected distances is greater than 201.20. All right. So again, we probably have to take from the sampling distribution of all of sample sizes 20. And if we were to take sample sizes of 20 and take the average mean of all those sample size 20, then we would have the sampling distribution of size 20, and that's what we would use, which basically means, if we're thinking about this correctly, let's take a look at the picture here. Now, we already know this is the normal distribution for the mean of adult females, the overhead reach of adult females. This is what it would look like. On average, adult females can reach 202, so on and so forth. The sampling distribution of 20 of those adult females, it's a little different. Like if we were to take the average height of 20, the average height of 20, it would still be a normal distribution. The mean would still be 202.5. The only difference is the standard deviation will not be 8.9 anymore. The standard deviation would be 8.9 divided by the square root of the sampling size that we've been using, which is 20 in this case. And so for that reason, we could still do this problem. If we wanted to calculate the probability of 201.2 or greater, then that's a little bit less than half. Let's say 201, and then everything greater. And so my lower bound would be 201.2. It says find the probability that the mean of the 20 randomly selected distances is greater than 201.2. So let's give this one a shot. Let's pull up our calculator here, and let's go with, I'm going to do a second entry, and I'm going to put in my lower bound, instead of 215, I'm going to put in 201, and then insert 0.2, comma, 1E99. The mean is still 202.5 because the sampling distributions of any sample size still will target it. And then for our deviation, it's going to be 8.9 divided by the square root of 20. And now you're going to have to close parentheses there. And what did we get? It looks like we got 0.7432 if we round it. So let's check and see if that works. Why can the normal distribution be used in part B even though the sample size does not exceed 30? Well, this is more of a technical question. Yeah, so it really all depends. So 20 is okay. It doesn't exceed 30, but what we could say was that the original data set was normally distributed. So if the original data set is normally distributed, the sampling distribution of any size will still be normal. So the normal distribution could be used because the mean is large? No. The normal distribution can be used because the finite population correction? No. The normal distribution can be used because the original population has a normal distribution? Yes. And then also the normal distribution can be used because the probability is specified. So it's C. All right. We got those down. we did this one similar in class. You're just going to do normal CDF, lower bound, upper bound, mean deviation for part 1. And part 2, let's try it really fast. We'll do second distribute number 2. In this case, lower bound 63.2, upper bound 64.2, my mean 63.3, and according to the problem, little sigma is 3.1. The standard deviation. And this is going to give us the probability of exactly 1 falls in this group. 0.1271. Not bad. Alright, so what if we had 19 women who were randomly selected and we had to find the probability that their mean weight of all 19 were between these two? So the values are the same. The lower bound and upper bound are still the same, but instead of just 1, we're talking about a group of 19. And so basically we can do second entry, and instead of 3.1 there, we can do the square root of 19. And then just close that off. So everything else still was the same. It's really nice. 0.4531. Same type of problem. First you find the probability of exactly 1, and then there'll probably be a group, probably a group of 12, and then you just keep going from there. So they're saying 170 and above, deviations 27, it's already normally distributed, everything's great. Let's keep going. Let's see here. Let's see if there were any questions. I'm not sure. Let me double check the chat. Did I miss 6.4? You did not miss 6.4. We've just started. We jumped in. We're doing 6.5, and then we'll look at 6.4. 6.4 should be pretty straightforward, especially if you got 6.2 and 6.3 down. 6.5 should come automatic to you. A ski gondola, wow, I don't even know, carries skiers to the top, so I think it's a ski lift. It bears a plaque stating that the maximum capacity is 16 people or 2,576 pounds. That capacity will be exceeded if 16 people have weights greater than that mean, which is 171. Assume that weights of passengers are normally distributed with a mean of 177.6 pounds and a standard deviation of 40.5 pounds. Completes parts A through C. So find the probability that if an individual passenger is randomly selected, their weight is greater than 161. So we'll do, okay. Yeah, I remember some people knocked 6.5 out really fast, and it was pretty straightforward. Well, that's just great. Let's do this problem, and we'll look at some of your problems. So I can't wait to see some of the problems that you may have. So just get ready, because we're going to do those problems. So let's try number 2 and find the probability that if an individual passenger is randomly selected, their weight will be greater than 161. So we're going from 161 as our lower bound, and our upper bound will be infinity. Not infinity, but a very large number. And then our mean is 177.6. And our deviation is 40.5. And what did we get? If we round it to 4 places, we're going to get 6591. 0.6591 should be good. Now, what if it says, find the probability that 16 randomly selected passengers will have a mean weight that is greater than 161? Hopefully it's less than 5%. So let's see what happens. Second entry. And what we'll do is take everything is the same, the lower bound, the mean, but the deviation of the sampling distribution is not 40.5. It's 40.5 divided by the square root of the sampling size, which in our case is 16. Yeah, 16. I could have just put in 4. Oh, well, it's point. I mean, it's like 95%. So it's like 5% that it will not happen. But this makes sense, okay? So the probability is really high that if you got 16 people in there, there's a chance that they have a mean weight greater than 161, which means it's at capacity. So we need to round this to 4 decimal places. It's 94, 94. That was it. Does the gondola appear to have the correct weight limit? I don't think it does. And the reason is because it's well, does it say you cannot exceed 16 people? But what if there is 16 people? So 16 people, actually you could say yes, it will, just because it's almost 95%. Does the gondola appear to have the correct weight limit? No, there's a high probability that it's going to be overloaded if it's occupied by 16 passengers. Yeah, that's what I was thinking as well. If there's 16 passengers, there's a great chance. It's an almost you could say a 95% chance that it will be overloaded. Um, no, there's a good chance that yes, the odds that every passenger will have a weight greater than 161 is low. Yes, only about half the I like the first one, to be honest. It just reads better. It didn't have the best weight limit, okay? That probability was very high. Alright, we're going to do a couple more from 6.5, and we're going to wrap it up. This video will be saved and put into our discussion menu, and you can study this, and hopefully this helps you. Kind of talking you through it, coaching you along, trying to show as much work as I can. So we have women have pulse rates that are normally distributed with a mean of 72.2 beats per minute and a standard deviation of 11.4 beats per minute. You need to complete parts A through C. First, part A. Find the percentiles of P1, the first percent, and the 99th percentile. Alright, so let's pull out our notebook here. And first of all, in a normal distribution, the first percentile, P1, corresponds to the bottom 1%. So what X value will give me the bottom 1%? And again, P99, this is the 99th percentile. That's also the top 1%. And that P99 is from here all the way down. First, let's do, what would this be? We're going to use inverse norm. Because we have the area, we have the proportion, 0.01, but we do not have the X value. So what we need to get is the mean and the deviation, and we're going to put that in there. So the mean is 72.2 beats. So let's do this. Second, distribute. Number 3. And the area is 0.01. The mean is 72.2. And our deviation is 11.4. And what did we get? So if your BPM is 45.6, you're in the lower percentile. 45.6 would be considered extremely low. We went around this off to one decimal place, so 45.7. I think I said 46, but 45.7 is what you needed to put in there. There we go. P to the 99. Well, I can actually just do a second entry, and instead of 0.01, put in 0.99. And we're getting, what did that say? If I round that off, I'm getting 98.7. All right. A doctor sees that exactly 25 patients each day. Find the probability that 25 randomly selected women have a mean pulse rate between 50 and 94. So we're going to do second, distribute. Number 2, 50, 94. The mean is 72.2. And the deviation is actually going to be 11.4 divided by the square root of 25, which is just 5. We're going to paste all this. Hit enter. It was so much that they said it was 1, so that's what they got. That's what I'm going to put down. See if it works. It actually worked. Okay, let's keep going through this. I think this was pretty helpful. Not much else really going on. I mean, all the problems are pretty much the same. Different scenarios. And then once you get to this part, the RA, it's just these types of problems are basically just kind of fill in the blank and stuff like that. Which of the following is not a conclusion of the central limit theorem? Oh, this will be a good problem to put on the final exam. Some question like this, right? Now, some of these questions aren't so clear too. Which of the following is not a conclusion? The mean of all the sampling means is the population mean. The distribution of the sample means will, as the sample size increases, approach a normal distribution. The distribution of the sampling data will approach a normal distribution as the sample size increases, or the standard deviation of all sample means is the population deviation divided by the square root of the sample size. I think C is no good. All the other ones seemed good. So there was a little tricky. We don't talk about the sample data. We talk about the sample means. Not the sample data, but the means of the sample sampling data, which is the sampling distribution there. That was a little tricky. Okay, let's jump to 6.4. And let's take a look at some of those questions from 6.4 and see how it goes. Hopefully it's not too laggy. Looks like the stream is is the quality is still a little laggy. So we'll have to correct that if it is. Alright, so we did do a few problems. Some of the problems we did not complete, but we did do some of them. Let's take a look and see what are some of the questions in 6.4. Three randomly households are surveyed. The number of people in the households are 1, 4, 10. Assume the sample size is n is 2 is randomly selected. Find the variance of each of the 9 samples. Then summarize the sampling distribution of the variances in a format of a table representing the probability distribution of the distinct variance values. So first we need to take the variance of each pair. Now it's kind of cumbersome to do this because it's such a small value and it's a little annoying, but let's just do it. So first, let's get in all those different pairs. We had 1, 1, 1, 4, 1, 10. Then we have 4, 1, 4, 4, 4, 10. And then it's 10, 1, 10, 4, 10, 10. So what I'm going to do is put the variance in each box. We need to see the variances of each one. So we simply need to take the variance. Now I already know the variance of this, because they're the same, the variance is going to be 0. The variance of this is going to be 0. The variance of this will be 0. Now I need to find the variance of 1, 4, 1, 10, and so on and so forth. Now to get the variance of these, there's quite a lot of different ways to do it, but I think the best way to do it is to just enter it into your calculator. So just do 1 and then 4, and then you just do second quit, and let's see, let's make sure I entered it in properly. I did. So now what I'm going to do is go into second stat, which is list. Go over to math, and number 8 is the variance. So I'm going to take the variance of L1. I got 4.5. So I can say that the variance for 1, 4 is 4.5, and it's also the same for 4, 1. So now I got to do 4, 10 and 10, 1. And 4, 10, 10, 1, yeah. And then I think we'll be done. So let's go back into stat, and this time we'll edit it, and instead of doing 4, 1, we'll do 10, 4. And I'm just going to do a second entry. I just forgot my list. What was the list I did? 10, 4. So 10, 4 turned out to be 18. And this one's also 18 then. So now let's do 1, 10 and 10, 1. And then we'll create our sampling distribution. We're almost done. So we go to stat. We go to edit. And we need 10, 1 this time. And just do a second. I'm gonna 40.5. So I come over here, 40.5 and 40.5. Now it's time to create a probability distribution with all of my results. So what we'll do, I'll make this be my x and I'll make this be my p of x. First I had 0, then I got 4.5, we also got 18, and then we have 40.5. Those are my results. Now how many zeros are there? 1, 2, 3 out of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 out of 9. 4 5s, I had 2 out of 9. 18, 2 out of 9. And 40.5, 2 out of 9. Alright, now 3 9s actually does reduce, but this does show that they all add up to one whole. 2, 4, 6, and 9 is 9, 1 over 9 over 9. So there's my probability distribution table. But I should reduce this to 1/3. So 1/3, 2 9s, 2 9s, 2 9s. And so now what we do is just enter this into the so I had 0, 4 5s, 18, 40.5, 1/3, 2 9s, 2 9s, 2 9s, and we got it. So when there's a question. When I try to find the variance for each, it kind of skips around. Hey, I'd love to see you do it. If, I don't know. You were using one-var stats? One-var stats doesn't give the variance. It actually, that's the one thing it cannot do. You could get the variance though by squaring the deviation. So like, for example, you saw the variance to be 40.5, right? Watch this. If I do use one-var stat, I got 6.3639. If you square this number, you will get the variance. 6.3639. So if I say 6.3669 or 3639, whatever it was, if I square it, I should get really close to the variance. But no, you have to get the variance, do it the way I just did it. Go in a second list and use the variance function, and then you'll be fine. It's going to be harder because it's going to be approximated. It's going to be harder to do that. Even if I try to get so I guess it would be a little hard, but yeah. But I thought you had mentioned that one was for sample and the other one was for population. These little guys here are the samples. So yeah, as far as one-var stats, are you talking about one-var stats? So if you go back into one-var stats and do it, yeah, Sx is the sample deviation, and little sigma x is the population deviation. So sample deviation, population deviation. If you want the variance of the sample, you have to square the sample deviation. I wouldn't yeah, I wouldn't try to go deeper than that. Just take that variance. This command here that I was showing you, um, yeah, this one. This gives you the sample variance. So that's the one you want to use when you're doing this homework section. You won't have any problems. You saw how fast I did it. Compare the population mean, or compare the population variance to the mean of the sample variances. They should be the same. Um, now the question is, well, how do you get the mean of this? Well, it's a lot of work to get the mean of this. You have to get two columns. Or take the average of all of this. You can take the average of all of this, add them all up and divide by 9. So like 4.5 is 9. 18 is 36. Plus 9 is 45. And then 40 is 81. Well, 45 and 81 is like 126 divided by 9. And we're getting like 18 or something like that. Some number. And then, or 19. And then is that the same as if we did the variance of 1, 4, 10? The variance of 1, 4, and 10. So if we go into stat and we go to edit and we put in 1, 4, and 10, it can be in any order, and then take the variance of it. We got 21. Will we get 21 if we add them all up and divide by 9? So if I add 4.5 plus 4.5 plus, I'll just do 18 times 2 plus 40.5 times 2. Divide by 9. Wait, 4.5, 18, 18. You have to divide by 0, 0, 0, 14, 0. I probably rushed and did this really fast, didn't I? And I'm dividing by 9. Four, 1, 2, 1, 2, 1. Everything's times 2. Let me go back there. So 14, 14. Da, 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 da. Oh, yeah. uh, uh, I did this is not correct. This is the variance of a sample, but in L1 it's not the sample. L1 is the entire population. So we'll do one var stat. And you see what we got for little sigma? That's our deviation. The square of this will be our variance. And so what I'll do is go into vars, go into stat, and use 4. That's the variance. Or this is the standard deviation now. All I gotta do is square it. and I got 14, which is what we got before. 14. So yes, 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 indeed. The population variance is equal to the mean of the sample variances there. Holly, I see what you're writing. Do you remember that it was done in class? I hope you remember, because it was. We did this exact same thing in class and it worked. So if you're not done, let's take a look at a couple more. I'll do one more, and this is the one that is on the quizzy. Call it the quizzy. I'm gonna find the one that's on the quizzy. It has to do with the girls. Let's see, let's go to it. Where is it at? We're gonna do the one that's on the quizzy. I think it's that one. Back up. When two births, yeah, we'll do this one. This will help you on the quizzy. But I think it's not going to be 2 births. I think it's going to be like 4 births. Let's see if we have another one. Nah. We'll do it. Let's go back. Let's do this one, and then we'll wrap it up. I think this will be good. Unless there's any other questions, you just type it into the chat. If you're watching this on your phone, pull up the chat or do something or send it into Canvas if there's any particular ones. But let's take a look at this. When 2 births are randomly selected, the sample space for genders are BB, BG, GB, GG. 4 different possibilities. Assume that those 4 outcomes are equally likely. Construct a table that describes the sampling distribution of the sample proportion of girls from 2 births. So, in 2 births, we got BB, BG, GB, GG. Now, the proportion of girls, the proportion of girls, not probability of girls. I just put this in here. It's 0. It's a half. Proportion of girls, a half again. And what's the proportion of girls? Well, there's 2 out of 2, so it's actually the proportion of girls is going to be 1. Now we're going to create a sampling distribution of those results. So we have our x, and then we have our p of x, and we're going to put in these values. It's 0, a half, and 1. Now, how many zeros did we get? 1 out of 4. A half, well, there's 2 out of 4, so that's actually a half. The probability of getting a half girl, actually, I should have put 0, 1, 2. Oh, okay, so we're actually doing a from the proportion of girls. So x is the proportion of girls, and then here's the probability. It's fine. And then 1, getting exactly the proportion of 1 girl, it's going to be 1 out of 4 chances to do that. So there it is. We have 0, 0, 1 half, 1 half, 1 half, 1 half. Let's see if this will accept this. This time we had 1/4, 1 half, and then a fourth again. And again, a fourth, a half, and a fourth will add up to 1. Does the mean of the sample proportions equal the proportion of girls in two births? Well, it will, all right? If we take the average of these and divide by 4, if we add them up and divide by 4, I get 2 over 4 is a half. I accidentally pushed the button. So that's what we're getting. The average of the proportions is a half. Now what about the average girls in all of the cases? If we do this, what would it be? It would be a half. The probability is still a half. Let's take a look. So yes, both of them will be a half. It's not biased. I mean, wait, does the result suggest that the sample is unbiased? As an unbiased? Yes, it is an unbiased estimator. It's not biased. There was a request for number 6 put out by Stephanie, so let's take a look and see if it's the same one. Oh, so 6.5? Let's jump around to 6.5. Number 6 from 6.5. And I may have done it earlier. I kind of did it a little backwards. I started with 6.5 first, and then we went to 6.4. Let's see, number 6. Uh-oh, must be a tough one. Women have head circumferences that are normally distributed with a mean of 23.26 and a standard deviation of 1.1. If a hat company produces women's hats so that they fit heads circumferences between 22.9 and 23.9, what is the probability of randomly selecting a woman will be able to fit one of these hats? So let's do this. We're going to do second. Let me clear this out. Second, distribute. And I'll start with number 2. And my lower bound will be 22.9. My upper bound will be 23.9. My mean of the women's hats will be 23.26. And the deviation is 1.1. And I'm getting 0.3479. I can't change this? Okay, let's move on to B. If the company wants to produce hats to fit all women's except for those with the smallest 3.75% and the largest 3.75% head circumference, what head circumferences should be accommodated? So let's look at a picture of this. This is the bottom 3.75%, and then this would be the top 3.75%. So I want to find x. I need to find x here and here. I need to find this x as well. We need to know what this is. And so what I'm going to do is I have the area, but I need to find the x, and so I got to use inverse norm with this little area piece. So let's see what happens there. The minimum head circumference is 3.75. So what we'll do is take out that calculator, and we're going to go with second inverse, or second distribute, go down to number 3, and it's the area to the left. So the percent is 3.75, but we have to enter that in as a decimal. So it's actually 0.0375. It can never be more than 1. The area cannot be more than 1. It's a percentage. And our mean, let's put in 23.26. Our deviation 1.1, and it's to the left. And I got 21.30 inches. They want me to round this to 2 places, so it's 2130. Now, the maximum head circumference. Well, the maximum is here on this side, but inverse norm, it doesn't work to the right. You have to enter it into the left. So what you can do is do 100 minus 3.75, which is like 66.25. So this area is 96. 96. 96.25. Everything to the left is 96.25 there. So now I probably could do to the right as well. I probably could have done to the right like this. Or enter in 0.9625 and just get rid of that tail. Now, this should work, 25.22. Hopefully this was clear. I feel like I didn't explain it that well. Was that clear? We get a thumbs up. Narifa is here. Let's see. If 18 women are randomly selected, what is the probability that their mean height circumference is between 22.9 and 23.9? So let's see what that is going to give us. We're going to do second distribute, number 2, and it depends on the calculator that you have. If you have the option of choosing to the right, but yes, you can do the max. The max can be done in 2 ways. It's best to subtract that 3.75 from 100 and put in 9675. That's the best way to do it, because that represents the area to the left. Okay, so since your calculator does not have that tell option, then you're going to have to subtract. To get the top, you need to figure out what is the area to the left, because inverse norm won't work from the top. It only works from the area to the left. So you'll have to subtract the top piece. If it said top 4%, you'll have to subtract the top 4% from 100. So now in this problem, let's go with 22.9. Was that clear, Stephanie? The mean is 23.26. And this time, yeah, no problem. So this time our standard deviation is not just 1.1, okay, because we're talking about a collection of 18 women. So it's going to be 1.1 divided by the square root of 18. And we're getting 0.9107. If this probability is high, does it suggest that in order for 18 hats, that an order of 18 hats will very likely fit each of 18 randomly selected women? Why or why not? Well, the probability that it will is 0.91. But also A is a good option too. The hats won't fit about 8.991% of these women. So now the hats must fit individual women, not the mean from 18 women. If all hats are made to fit head circumferences 22.9 and 23.9, the hats won't fit about 8.91% of those women. So I like A actually as a best choice. Oh wait. Why am I getting it? I think I just psyched myself out. I didn't even read this one. Yeah, I didn't I just clicked on these really fast. This is like kind of a tricky question. It says the probability that in order of 18 hats will very likely fit each of 18 selected women is 0.91. Trying to see the original question now. If this probability is, the probability is 0.91. If this probability is high, does it suggest that an order of 18 hats will very likely fit each of 18 randomly selected women? Why or why not? And they're saying no, the hats must fit individual women, not the mean from 18 women. If all hats are made to fit head circumferences between 2.9 and 3.9. The hats won't fit about half of those women. Okay. Yeah, we didn't read that last one question carefully enough, but it was good. You saw the answer now. All right. Any more questions on that? It was pretty rough. Some of those questions are pretty tough. All right, we're probably going to wrap it up. Stream has lasted for an hour. We're going to come back later on with chapter 7, 7.2. Any other questions before we take off? I think I do have a question that just popped up. Let me check over here. I'll be live streaming 7.2 around 6 o'clock. Actually, no, it can't be 6. We're going to make it 8 o'clock. Maybe not even. Maybe I'll send out a message about that. We will definitely be live streaming soon. I'm glad this was helpful. Hang in there. Just keep doing those problems. Get better and better at this stuff. And it's going to be great to be done. It's going to feel really good to be done, guys. Honestly. Get you that quiz. I want to see some high scores on that quiz. 100 minutes. I want to see some really, really high scores on it. Alright guys, we're going to wrap it up here. Hopefully this information has been helpful to you, and you should do really well in the future, guys. That quiz has been open. It's been open. It is open and it is ready. Do a good job on it. Talk to you soon. Bye bye.